Okay guys, this is going to be a very quick tutorial on Hardy-Weinberg equilibrium. Okay. Alright, so first we're going to probably want to go over the 5 things that must be true for Hardy-Weinberg equilibrium to be true. And they're listed right here. They are: no mutation must occur so that no new alleles. What the fudge did I type? No mutations must occur so that no new alleles do not enter the pop. Okay, that's a double negative, I'm pretty sure. But basically, what it's saying is you can't have mutations because otherwise it introduces new alleles, and that would violate Hardy-Weinberg. Because that's introducing genetic variation, and Hardy-Weinberg is about assuming genetic variation is absolutely stable. Next one is no gene flow. So, and when you think of gene flow, that's basically like migration, when things come in and come out. Yeah, so like, let's say like a group of horses leaves the large herd to go somewhere else. That would be leaving, and that would be gene flow, and you can't have that. Hardy-Weinberg. You have to have random mating. It has to be completely random. Like, there is no selection about mates. They're just, if it's a male and a female, there's no preference, they just get put together. The population must be so large that no genetic drift happens, and so this technically, a population can never technically be large enough for genetic drift to happen. You can just approach not having genetic drift, but you would have to have technically an infinitely large population for it to have no genetic drift. But effectively, you, in practical standards, if you had like, let's say, a population of like 100,000 or something like that, it's like effectively zero. So then, yeah, there should be no genetic drift caused by random chance. And then no selection can occur so that certain alleles are not selected for or against. So basically, what this is saying is you can't have natural selection. Natural selection is not allowed in Hardy-Weinberg. Okay, so with those 5 base things, we can now actually do some questions of Hardy-Weinberg. The 2 equations that you must know to do Hardy-Weinberg are pretty simple. They are, the initial one is P plus Q equals 1, and the other one's P squared plus 2PQ plus Q squared equals 1. Now you might be wondering what P represents and Q represents. Technically they're interchangeable since they're both just variables, but generally P represents the dominant allele. The dominant. While Q represents the recessive. Of course, they aren't necessarily dominant recessive. This is just in general cases. It could be actually co-dominant, all that stuff, but generally it's going to be dominant first, then recessive. Okay. So, with these 2 equations, now you can actually do the questions with it. So let's look at a question. Here's an example that I found online. I'll give you the link later if you want to see more questions. They have like 11 of them that you can do. If doing like 1 question is not enough for you, I'll actually probably go over 2 of them, but then if you need more, you can just go onto the actual website that I found them. I'll just post it in the Excel, and I guess I'll upload the Excel as well. Okay, so let's go for the first question. So you know that a sample population in which you know that the percentage of homozygous recessive genotype, which is little a, is 36%. Using that 36%, calculate the following. The frequency of AA genotype. Okay, that should be simple. They gave you the percentage. The frequency of AA genotype is just the 36% again. because that is the percentage of, that is the frequency of the genotype A, because it says this is a percentage of the homozygous recessive genotype. Okay, what is B then? B is now asking for what is the frequency of the A allele. Now, this is not talking about the AA. What it's talking about is how common is the allele itself. This is when there's going to be some math involved. So, Q squared and P squared, in the case of, you're going to usually use Q squared because they're usually going to give you the recessive thing. If they give you the genotype of the recessive, Q squared is equal to the given number, in this case 36%. So for 0.36 is equal to Q squared. So then, square rooting 0.36, we arrive at the fact that Q is equal to 0.6. So the frequency of the A allele is 0.6. Or 60%, whatever you like to use. Then we have the next one. The frequency of the A allele, like the capital one. Now, there's two ways of doing this. You can do the complicated way and plug Q that you calculated back into this equation. But that's dumb because then you have to go do a quadratic formula, and who has time for that? Or you can just do the simple thing and just plug it into the top equation. P is what you want, Q is you found out, so P plus 0.6 equals 1, P equals 0.4. So that's the answer for C. It's 40%. So then, now you want the frequency of the genotype AA and a little a. So to do this, we just go back to the top equations again. As you saw earlier, Q squared equals the given value, so P squared obviously should give you the value, should give you the homozygous dominant genotype. So, since we know what P squared is, it's 0.4. Just do 0.4 squared. And that is equal to 0.16. And so you have a 16% chance of getting AA. But now you want to get the homozygous as well. To calculate the homozygous, just plug numbers into the equations basically. Either that or you can solve for 2PQ. Both, because since now that you have this value and this value, you could technically plug them back in, which happen to be 0.36 and 0.16. And then this value, if you isolate for this value, that is the amount, that is the frequency of AA, but I generally won't do that. I'll usually just use a equation up here, so it would be 2 times 0.6 times 0.4. So 0.6 times 0.4 is 2.4 times 2 is 4.8, 0.48, which equals 0.48 for a little a. And then to check your work, you can just see if they add up correctly. 0.16 plus 0.48 plus 0.36. Oh wait. The fuck? What the fuck did I fuck up? Oh no, no. I didn't fuck up. What the hell am I talking about? That does equal 1. Stupid me, I can't add anymore. Okay, yeah, so that adds up to 1. So that means your answers are correct. So then we go on to E. The frequencies of the two possible phenotypes if A is completely dominant over A. So, we're going back to a standard dominant recessive trait. Now we're talking about phenotyping. So, if A is completely dominant over little a, capital A is completely dominant over lowercase a, that means as long as there's one capital A, that will take priority. So, there's two cases where that would be. It's either you have both capital A or you have a capital A lowercase a. And based on our earlier values, we found that having both capital A's is 0.6, and we found having a capital 1 and a lowercase is 0.48. So basically you just do 0.16 plus 0.48 to solve that, and that would equal okay, I'll do this for carry over 64%. So 0.64. And there you go. That is how you do it. You do a Hardy-Weinberg question. Okay, so I guess I'll do one more. This one will be dealing with sickle cell anemia, I think, is the next one on the list. So let's look at the sickle cell anemia one. So yeah, we did problem 1, here's problem 2. Sickle cell anemia is an interesting genetic disease. Normal homozygous individuals, capital S, have normal blood cells that are easily infected with the malarial parasite. Thus, many of these individuals become very ill from the parasite and many die. Individuals homozygous for the sickle cell trait, lowercase s, have red blood cells that readily collapse when deoxygenated. Although malaria can't grow in these red blood cells, individuals often die because of the genetic defect. However, individuals with the heterozygous condition, capital S, lowercase s, have some sickling of the red blood cells, but generally not enough to cause mortality. In addition, malaria can't survive well within the partially defective red blood cells. For us, heterozygotes tend to survive better than either of the homozygous conditions. If 9% of the African population is born with a severe form of sickle cell anemia, lowercase s, what percentage of the population will be more resistant to malaria because they are heterozygous for the sickle cell anemia gene? Okay. First, they gave you a lot of bullshit that you totally don't need. So first, what you probably want to do is cut out everything that's irrelevant and just look for what's actually useful. The only things that are really useful are the fact that lowercase s, okay, just realize these are lowercase because it's hard to differentiate them, is equal to 0.9, oh, not 0.9, 0.09, and you're trying to solve for what is the percentage of capital S, lowercase s. That is the percentage you're looking for. So, how do we do this? Let's go back to the two equations that we know. P plus Q equals 1 and P squared plus 2PQ plus Q squared equals 1. Using that, we can then begin solving it. So what do we know for stuff off? We know that it's 0.09. So what does that tell us? It tells us that 0.09 is equal to Q squared. So to solve for Q, just square root it. The square root of 0.09 is equal to Q. And the square root of that is equal to 0.3 is equal to Q. Okay, so now you have the Q value, which is helpful because now we can actually basically find what the P value is, because we'll need to know the P value as well to solve for the heterozygous. So using the P plus Q equals 1, we can then solve for it. So it's basically, we know what Q is, so P plus 0.03, not 0.03, 0.3 is equal to 1. So then P is equal to 0.7. Okay, now that it's 0.3 and 0.7, we can then begin to actually solve for heterozygous, because remember that the heterozygous is represented by the 2PQ. So with those two values, we just solve for 2PQ. What is 2PQ? So the S, lowercase s, is equal to 2 times 0.7 times 0.3. And what does that equal? That is equal to 0.21 times 2, so 0.42. So you have a 42% chance of being a heterozygous individual with sickle cell anemia, assuming that the Hardy-Weinberg equation is valid in this case, which of course it probably isn't, because let's go over some of the things that obviously aren't true. Probability is there are people moving around, so there probably is migration. Probability is that's not random mating. You mate with people you like. You're not just going to go up to a random person and ask them, can I mate with you? And the population might be pretty large, so that genetic, like this might be valid, possibly. And natural selection is almost always occurring. In this case, it actually is basically occurring because, once again, malaria. Malaria is actually introduced, forcing us to not follow a standard distribution and actually increase the zygote amount, because these zygotes are more likely to survive. And of course, mutations are always occurring, so yeah. Most of this is actually wrong if you actually want to do a true pretty much Hardy-Weinberg in real life is pretty much inapplicable to everything, but it's useful in biology because you can use it as a baseline to compare against. So if you do see some sort of change that's not seen by Hardy-Weinberg, you can now begin to investigate what is causing that change. So yeah, that is Hardy-Weinberg for you. All right, bye guys.